Good morning, everyone. I'm Jamel Saadaoui, full professor of economics at the University of Paris 8, a small university in the north of Paris. We are going to cover today in this video the structural VR models estimated with data with different identification schemes. So I encourage you to go to my website where I present some of my research here. So first, we are going to look in my website, Econometrics SVR, and you will see that we have a series of blog here about SVR. So we are going to cover this blog today. And in particular, we are going to look at the Stata package VR_NR for narrative restrictions, crafted by Abigail Pushek, Jona Danzinger, and Christopher Koch. So let us dive in. So I will start by open do file, as always. So I use an appropriate display for the windows. So I could select this. Okay. So please be aware that all of these files are available on my GitHub. You can find it at the end of this blog. So you can go here and you can select the blog, which is here, and all these files are available here. No, sorry, this is for a RATS version, so it's not another one. So here, yes. So everything is here, okay? So everything is also explained into the blog, so you can also go to a blog to have a look. So first, we are going to so we are going to install the package. My package is already installed, but for the demonstration, I will install it here. As you can see here, the package is already installed because I did that procedure before. So if you remember the code, you don't need to install it a second time, so you can come up with that. So I clear the console of the data and I drop all the previous graphs. In my application, I use PNG format for the graph, but you can choose another one. So graph drop underscore all is for erasing all the graphs. You can choose the current directory. For me, it's here. And we are going to open a log. So first line here, capture log close. It will close log close. It will close all the logs. For example, I could add log close underscore all. Yeah. So I open a log. I can do it. Yes. So it starts this log. And at the end, we have a text file, but you can see everything that you do. I also encourage you to read the help of the package. You explain that you will use a VR command of Stata and will pass all of the results into meta functions. And I encourage you to explore a bit here. So you have also, for example, you have this example, but we are not going to use it now, but it runs here. But so if you click here, the shortened example will be done. Okay, so we are not going to explore it now, but we can we're going to look at it afterwards. So be patient. We are going to look at it later. But we can see that if you click here on the help, the code will be automatically done. And you can also see that this example of a short one, which is a Stata example, is available on my GitHub here. Okay. So first it produces all the impulse response functions, and then it produces the forward forecast error of variance decomposition, and then at the end it will do the historical decomposition. So E is just for the short-run restrictions. So short-run restriction apply no reaction during the same quarters. So you see that, yeah. Starts 0 here, starting 0 here and here. So it's the shortest key. It's the recursive ordering that you see in several papers. But of course, this restriction had to be justified from a theoretical point. So keep in mind that the option ident is for identification. So you will have short-run restrictions, 0 long-run restrictions, and narrative sign restrictions. So if you have short-run restrictions, it will be 0 according to a recursive ordering. If you should use Blanchard and Qua BQ, it will be 0 in the long run. So for example, you can argue that the neutrality of money is true, and you can also have a short-run restriction here where you can include some theory behind it. So let us start with a long-run restriction. So we clear the data first. We use the long-run data and the date as the time series identifier. Again, all this data is available here. So the data for the long run is available here. Yeah. So what we have is a series of GDP growth and unemployment change for more than 100 quarters. Okay, from 1948 to 7 quarters to 1978 at the end of 1978. Okay, it's for the US economy. So first you estimate the VAR, and then you use the VR function with a BQ identification, specify the VAR, that is a VAR, the name of the VAR, and the option, the name of the options. And then you can also display the options with a name that you give for the options, which is here. And you can display everything. Let us run that. Of the VAR estimated, you have options, identification, the horizon. You can change if you want to have a different thing for the shock as a one standard deviation or as a unitary shock. And you have also other options like for the bootstrap and saving. For example, I will not use it here, but you can change the option here. For example, by changing the format here, or changing the confidence intervals for the input resolutions. So if you're interested in changing the options, you can go and see this function and using the appropriate options will change these different things that you want to change for your application. Okay. So the code is here. So the name of the VAR is VER, which is selected here. The name of our options is ops, we selected here. I will also use this meta function to make the area impulse response function length, and then I will make the plot here. I will do the same for the forecast or variance decomposition, name of the VAR, options, use a meta function to make the estimation, to have a band, and then for plotting. Yes. And for historical decomposition is the same. So I estimate the VAR with the options, and then so let us select everything that is between meta and end and make the estimation. So what we have here is the reaction of GDP growth to shock on exogenous shock to GDP growth. So as you can see, that one standard deviation is around 0.08, and unemployment reacts to a shock on GDP growth. It reacts by having an increase at first, which is strange. Oh, sorry, no, that's not strange because we have long run restrictions. So here we are not in the short run restriction, sorry. It just constrained the impulse response function to go to 0, which is what we have here. But still, yeah. Again, first we have a shock on the GDP growth. It reduces the shock of unemployment, increase in employment, it reduces GDP. And you can see that one standard deviation of unemployment is around 0.2, and at the end is equal to 0. You have a forecast error decomposition, and you can see that most of the forecasted error variance is due to GDP growth. The same to unemployment, sorry, and here you have employment, which is explained by unemployment. Look at the composition. You can see that growth can be decomposed into historical shocks. Some of the shocks on GDP growth and unemployment, and most of the time, GDP growth variation or dynamics is explained by shocks on unemployment. If you do the historical decomposition about unemployment, and you can see that most of the time growth, shocks on growth, exogenous shocks on growth, explain part of it, but most of the time it is shock on unemployment, which is consistent with what we have in the forecast or variance decomposition. Okay, so that was for the zero long run restriction. So I repeat, when you impose zero long run restriction, basically you said in the long run, after 40 quarters, you don't have any reaction of GDP growth to shocks on GDP growth, of unemployment to shocks on GDP growth, to GDP growth to shocks on unemployment, and to unemployment to shocks on unemployment. Okay? So now we are going to go to narrative sign restrictions. So for narrative sign restrictions, the writing is a bit different. So I will start that again. The right references is coming from this Ambrogio Bianchi's SVAR toolbox coming. So Ambrogio Bianchi's is Bank of England, if I remember well, and the code is following the notations of Kilian and Luc de Paul's book, very excellent book of 2016. So clear the data. So let us see what is happening when I do that. So clear the data. Oof. Data clear. Use the data set for the sign restrictions. So now we have logarithm of inflation, logarithm of the Fed funds, and logarithm of unemployment for more than 160 quarters from the 60s to the beginning of the 2000s. Yes? And yes, so I can close that. I will also close the help and no, okay. So use the date as the identifier. So it understood that I have data over this time span, and the delta is 1 quarter. So I estimate the VER as in the Stata syntax. Nothing new, and then I will change. So now I will have a short-run restriction here. The name of the var is V, the name of the function is ops. I add a linear trend. This linear trend is already there into the data. Yes? Which is exogenous. So narrative restriction is you have during the Paul Volcker disinflation, the narrative restriction which say that during that time the inflation should have been reduced by the action of Paul Volcker. Yeah. Let me add a vertical line. So use display. Use the date what you want to make a vertical line. Should give you a number. So it's 79 quarters after after 1960, the first quarter of 1960. Oh yes, sorry. So you can see that we have a narrative restriction saying that the action of the central bank has produced an increase in inflation, which seems to be, by eyeballing it, quite understandable and quite reasonable. Okay. So go back to what we have. So I do it again. I can also show the options as before. So now short-run restriction, the shock is just one standard deviation, 95% for the confidence band. I can change it if I want. I will show you how to change it later. We can set the options here. The draws for the native time restriction, the maximum failed time restriction draws. You can change that also. And the progress. So we are going to progress for each backup draw. So as we use a local variable, you have to run that together with the meta code. I will just show you how the meta code. So create a time restriction, which is V. You set the monetary policy shock to positive monetary shock, log the matrices. A supply shock decrease inflation, decrease in employment, and a supply shock also decrease the Fed funds. A double shock should increase inflation, reduce unemployment, and you have a reaction of the central bank. Monetary policy shock, in theory, should reduce inflation but increase unemployment, and of course, it's a positive monetary policy shock, so it's an increase in the Fed funds. You are going to set the options by making option set, number of draws, 1,000. Do Stata have to, meta have to display the frequency of updating? Yes, and the frequency is 1,000. I changed the confidence interval to 68. So the main routine that made the calculations and store into this object is this one. And so the name of the var, the shock, the options, and what we have created here for the narrative restriction. So now we can estimate the impulse response functions using these and give it this name. The forward error variance decomposition. Keep in mind that the VR is this name, option R is name. Using this function, I can, by selecting the appropriate option, having the historical decomposition. So you can use this function to plot and save the impulse response function. It's quite good here. And I will keep a median impulse response function, and we can keep a band. I will show you how to export the bands later. So run everything between meta and end. So we can see that the options have been changed here at 68. I can change between bootstrap and one bootstrap, but we didn't. So it is estimating the different draws to see if the restrictions are accepted by the data. So it's a Bayesian estimate, if you want to. So he's computing the input response function. It's done. The forward error variance decomposition, forecast error variance decomposition, sorry. So now the plots are done. So it was quite fast, actually. So we have 3 variables on the system. So we are going to have 3 times 3 set of input response functions. Three graphs for the forecast error variance decomposition. And 3 graphs for the historical decomposition. So let us start with supply shock. So the supply shock reduce inflation, reduce unemployment, and does not require a strong answer from the monetary policy. Demand shock, increase inflation, decrease unemployment as predicted by the theory, and imply that the reaction from monetary authority to reduce inflation. And of course, the monetary policy shock is reducing inflation because that's the target. It creates a bit of unemployment and it is materialized by an increase in the Stefan rates. If you look at the forecast variance decomposition for the supply shock, it explains half of the inflation dynamics. Demand shocks is less, and monetary policy shock is about 40%. For unemployment, supply shocks and monetary policy shock are explaining a lot from the forecast variance decomposition for unemployment. And for monetary policy, no surprise, it is driven by, of course, monetary policy shocks and by supply shocks. So, for example, inflation was driven a lot by demand shocks in the 80s. That's not surprising. Unemployment was driven a lot by demand shocks in the 80s. At the beginning, end of the 80s and beginning of the 90s. And in the 80s, the monetary policy reaction was to fight demand-driven shocks. We can close that. So lastly, I will show you how to do the zero short-run restriction. So zero short-run restriction is quite clear again. Let us look at the data first. So clear the data. Data are clear. Use the data from short-run. So we have inflation, unemployment, Fed funds, trend, and the quadratic trend. So for the US economy, and the period is the same. So let's declare the data as time series data. And now estimate the VR with Stata syntax. If you want to, so you name the bar and you include that you are going to use OI R, which is the short-run restriction option. The name of the option are A, linear trend, quadratic trend. You can display the options if you want. So you have all the options. Now you can see that the identification is OIR. So in Mata, you can also display the options like that, use the plus function to have the liking the Bloch-like part, there are long-run restrictions, so the writing is the same. So I'm going a bit fast on that. So here you have 3 variables, so 3 times 3 input response function graph, 3 graphs for the forecast error variance decomposition, and 3 graphs for the historical decomposition. And I choose the clean plot scheme for the graph, which is made by, which is quite convenient for this kind of analysis, because you have a nice grid and you can see directly the numerical numbers. So, for example, if you go to the last graph and to see the Fed fund reaction after shock on Fed funds reaction of inflation, employment, and Fed funds, what you can see is that you can see the ordering of a model, because inflation does not react conversely to Fed fund, unemployment neither. If you go to unemployment, you will see that inflation does not react conversely to unemployment. And if you go to inflation, you see that, of course, inflation and unemployment react conversely to Fed funds and unemployment. So the ordering is like that. So first you have inflation, then you have unemployment, and then you have a Fed fund. So forecast error decomposition, inflation is reacting to inflation shocks. Unemployment is also reacting to inflation for a large part, which is non-negligible. And for the Fed funds, they react to inflation, but more to unemployment, even if the confidence interval overlaps. So inflation is explained by shock on inflation itself during the 70s, which is in line with oil shocks during that time. So the 2 big oil shocks in the 70s. So inflation is explained by itself. And after the end, during the end of the 90s, the inflation is driven by shocks on unemployment. Unemployment was caused a lot by inflation shocks during the 70s, and it was reduced by shock on unemployment at the end of the 90s. And the Fed funds was fighting inflation as explained by historical shocks in the 70s and by unemployment. So we can close that. Okay, so now what we are going to do is a small extension of this block. So everything is explained here if you want. So what we are going to do is to look at a small extension of this block that I did in April. And a small extension will show you how to have numbers for the long-run restriction scenario. So I will run this time only the part of meta here for the impulse response function band. So I can skip that part, and I can skip that part too, actually. So let me clear everything, use the data, declare the time series, I estimate a VR using, I estimate with a package. I declare that I use a BQ, Blanchard & Coire. The VAR is called VAR, the option is option, and I can show the option here. So I can change the option if I want, but I will not here. I will save a function. We can improve the bit of coding here. So I will save the results with meta functions. So the meta functions are this one and this. Okay. I have just to run that. Then you will compute the IRF bound and plot it. So you will have here. Okay. So where I can find this number for those graphs. So I open my data. So what I can do is to list the matrix in memory. What are the kind of matrix I have? So I have the impulse response functions, and I will also have the impulse response function as number here. Let me check here what we can do. Actually, instead of using IRF, I can use this one. Let us stick to what we have here. So what we have here, we have the numbers for the impulse response functions. So maybe we can use an appropriate display for the windows. So here the response to GDP growth shock starts at 0.8. So you have a number here, 0.8, and then it goes to 0. For the second one, it starts at 0.22. So you have it here. For the third one, it starts at minus 0.9. So you have it here. And for the fourth one, it starts at 0.2. So you have it here. Okay. So I will list the lower bounds for the confidence interval here. So you have it here for the first two impulse response functions. So you have it here, minus 9, which is, I think, this one. And you have it minus 0.8, which is here, okay? So I will also do that. Oh, there is something that I didn't show you. I will show it to you. So it will store, so that's something that it is in the, for example, if you want to be very precise and to keep focusing on only one response. For example, the response of growth. So what you are going to do, you are going to add this option, okay? And this option, you are going to add it here, okay? Why you are going to do that, I will explain you that later. So let me close that. Yes. So rerun everything again. So now what we have the first impulse response function, which is on the left here. Maybe just the second impulse response function, which is here. You have also the third and the fourth. We are not interested in now, but you will have now the lower bound, minus 0.45, 0.8, and you have it 0.5 here and 0.32. Sorry, minus 0.45 and 0.55. 0.8 0.08, sorry, and 0.02. So if you want to have real numbers for the bands, you can do it, but you have to, if you don't want to code evilly, to focus only on one shock, which you have done by using that. But if you are not interested in that, you can do all the shocks. So now I will do something that I don't test it because I may, but I will recommend you to go to this version of this new version of. So if you want to keep a band, if you want to keep a band in the impulse response function, you can go to the part with the native sign restriction, and you can replace something here. Yes, if you want to do that, something that Matteo Fargaria from ECB told me, it works. So you can replace it somewhere, but I didn't test it, so I encourage you to test it. But it should be doable to do it because I think I did it here, so it should be okay. Let me check. If we do that, do we have? Let me check. Okay, we are going to do that, and I'm surely going to do a new blog about it, but we will see what are the what is saved into these matrices. If I follow the logic of the previous code, it should save a band for impulse response function, for forecast error, forecast error variance decomposition into temporary matrices. So if you keep the free variables, the free variables, it will keep the bands for the last variable. It should be like that, but I'm not sure because I never tested it. So more work is necessary here, but at least to conclude that we can see what we have into the memory and maybe try. So I think that's the same logic in a sense, but we can check. We can check by looking at that. So let's go. So what we have here, okay, so we have more than, yes. So the temporary matrices, I think they will do it for the last variable. So if you want to do it for one variable, you have to do, to select only one response, for example. So let me just check what we have here. So in theory, it should be that. So the reaction is -2, and after it fades away. Here it's very small. So it is this one. Or let me again use appropriate set for. And this one is start at 0.5, so it is here. Okay. So here we have the free input response function for the last variable in the system. Okay. So what we have in terms of, I think it is not the band for the, but maybe if we simplify, let me do something. Let me simplify that by just following the same logic, keeping only one variable. We are going to keep only one variable and save and compute only the input response functions. So how I can do that? I can do that by using the options. So I hope it would work, but I don't know exactly. They tried. So options, it should be written like that. We will see. And it is a meta option, so I have to put it after meta. I will only do the input response functions. And okay, here I don't need that. So let me try. Yes, maybe it should be like that. But the name of the variables, we are going to focus on inflation reaction. Okay, and then I will do what I just did here. But we can do that. It's not so complex. Okay, let us try. And now we are going to plot only the reaction of inflation should be faster. We focus on inverse response function, so we are not computing these two guys. And plot and save. Okay. Let's go. So it seems to have worked, so I'm surprised. That's a good news. So now that's good because we have clearly what we want to have. So let me do it here. That's quite a nice update, I suppose. Okay, so we have an input response function as before. And we have a confidence band, so we should have 6 confidence bands. So we have the lower bound here for this one, the lower bound here for this one, the lower bound here for this one, the lower bound here, the upper bound here for this one, the upper bound here for this one, and the upper bound here for this. So I think we made something correct here. You can save it if you are interested in. So I suppose that's a good improvement for this code, and I will justify to make a video on that, and I hope it will be useful for you. So again, if you want to keep another variable and to see the true numbers for the input response function, for example, you can follow the same procedure as you have here. So I'm quite surprised it worked, but sometimes it works. I didn't show you how to save a graph PNG because using these options that I didn't show you, especially this one, may create some error messages. So if you want to save it, I recommend to use the names of the graph and save it with a Stata normal coding afterwards, because the graph will be into the memory of Stata, so you can afterwards save it it is fine. So thank you very much for your attention. So please go to my website and quote these two blogs if you are interested in that. We have it here and this one. So I hope it will be useful. You can also go to my GitHub and you have all of the files here. So I stop here. Thank you very much for your attention, and I hope that it will be helpful for some of you. I like to learn. We can learn together. Thank you very much. Have fun.